So in this video, we're going to cover the spanning sets of vectors, or identify when a set of vectors spans a vector space. So here's the idea. If we start with the vector space S, and then from that vector space we extract n vectors, we say that those n vectors span the vector space if for any arbitrary vector S that we have in the vector space, right? For any vector S, if we can write the vector S as a linear combination of those n vectors, then we say that the vectors form a spanning set for the vector space. So here's an example of my pen freezing up on me right in the middle of a lecture video. There we go. We'll see if we can make it through this one, or if I'm going to have to restart my computer. So let's say we have the vector space R2. Vectors in the vector space R2 are going to be arbitrary two-component vectors. So they're going to look like x sub 1, x sub 2. So if we take the set of two vectors from R2 that look like this, the vector 1, 0 and the vector 0, 1, what we can show is that this set of vectors spans the vector space R2 because any arbitrary vector in R2 can be expressed in terms of these two vectors. So for example, if we write x sub 1 times the vector 1, 0 plus x sub 2 times the vector 0, 1, so here we have a linear combination of these two vectors, this sum will add up to the vector x sub 1, x sub 2. So every vector in R2 has a simple linear combination that represents it in the vector space R2 using these two vectors. But this isn't the only set of two vectors that spans R2. In fact, there's infinitely many sets of vectors that would span R2. So for example, another one that would work would be taking opposite of 1, 0, comma 0 opposite of 1. This set of vectors also spans R2 because if we grab an arbitrary vector from R2, we can write this vector as a linear combination of these two vectors like this. The vector x sub 1, x sub 2 from R2, the arbitrary vector in R2, can be written as the opposite of x sub 1 times negative 1, 0 plus the opposite of x sub 2 times 0, negative 1. If we do this vector summation, we'll get back this vector right here. So because this vector is arbitrary, it's not a specific vector, we know that we've demonstrated that every vector can be written as a linear combination of these two vectors. In R3, an arbitrary vector would look like ABC, or x sub 1, x sub 2, x sub 3, where x sub 1, x sub 2, x sub 3 are just real numbers. And the set of vectors given by 1, 0, 0, 0, 1, 0, 0, 0, 1 would span the vector space R3, because if we have an arbitrary vector x sub 1, x sub 2, x sub 3 in R3, we can express it as a linear combination of these three vectors very simply as x sub 1 times the vector 1, 0, 0 plus x sub 2 times the vector 0, 1, 0 plus x sub 3 times the vector 0, 0, 1. And we've done some nice examples here, but the vectors don't need to be quite as nice. So for example, here's a set of two vectors in the vector space R2, and the question would be, can we express any arbitrary vector x sub 1, x sub 2 as a linear combination of these two? And the answer is going to be yes. And what we could do is take advantage of the fact that we can represent these using column vectors. So we could say, hey, we need to find c sub 1 and c sub 2. We need to see if there exists scalars c sub 1 and c sub 2 such that c sub 1 times 1, 1 plus c sub 2 times 2, 1 is going to be equal to the arbitrary vector x sub 1, x sub 2. In other words, given any arbitrary vector in R2, can we express that vector as a linear combination of the vectors 1, 1 and 2, 1? And I wrote it in column form to hint at what we would need to do to figure this out, we would just take this thing and put it into an augmented matrix, because this is a system of two equations. The rows represent equations, and two variables. The c sub 1 and the c sub 2 are the variables. So we just augment this with x sub 1 and x sub 2, and then we could put it into reduced row echelon form. So for example, we could say, hey, take the opposite of row 1, add it to row 2, replace row 2 with the result, and that would give us a 1, 0. Then opposite of 2 would be negative 2, plus 1 would be negative 1, so we'd get 2, negative 1. Here the x sub 1 wouldn't change. The opposite of x sub 1 plus x sub 2 is going to be x sub 2 minus x sub 1. And then I could do two row operations here. We could do twice row 2 plus row 1 to get a 0 in this spot. And we could do the opposite of row 2 to get into reduced row echelon form. So if we do that, we're going to get 2 times row 2 plus row 1. So we're going to get the 1, 0 here. 2 times negative 1 is negative 2 plus 2 is 0. And then 2 times x sub 2 is going to be 2x sub 2. 2 times minus x sub 1 is minus 2x sub 1. Plus x sub 1 is minus x sub 1. And then the opposite of row 2 is going to be a 1. And that will flip these, so we'll get x sub 1 minus x sub 2. And now we're in reduced row echelon form. So we can see immediately, we recognize this is the c sub 1 column, this is the c sub 2 column. So indeed, we're able to find that if we let c sub 1 equal 2 times x sub 2 minus x sub 1, and c sub 2 equal x sub 1 minus x sub 2, we'll be able to write any x sub 1, x sub 2 as a linear combination of 1, 1, and 2, 1. So it is the case that these two vectors span the vector space that we have. It's not always the case that vectors will. So for example, if we start with the vector 1, 0 and the vector 2, 0, for example, just a simple example, and we tried to span the vector space, we'd run into problems, because we would have, hey, we need to find c sub 1 times 1, 0 plus c sub 2 times 2, 0, so that it adds up to the vector x sub 1, x sub 2. And when we do this, we get c sub 1 plus 2c sub 2 equals x sub 1, and then we get c sub 1 times 0 plus c sub 2 times 0, which is just 0, has to be x sub 2. And so the only time that we could solve, the only time this would be true would be for x sub 2 to always be 0, right? We just determined if we use these two, x sub 2 would need to always be 0. So there'd be infinitely many vectors in the vector space R2 that couldn't be represented. Anything with something other than 0 in the y component would not have, we would not be able to express it as a linear combination of these two vectors. So this would be a case where this set of two vectors does not span the vector space R2.